Okay, so before we get back into commutation, I'm curious of what your thoughts were of the tour. I didn't get to do the tour with all of you, obviously, because we split up in two groups. Did you find it interesting, seeing the motors? And I mean, it's a different perspective because it actually shows you how they rebuild the motors, but actually when we talk about, and they didn't have a ton, they only had one induction motor that he talked about. It was on the test stand when we were there, but you saw the rotors, the stators. We talked about, in our group, we talked about the armature and the field winding, and it was a DC field, right? So you could put it in shunt or in series. And then he talked about compound. I don't know if Dave talked about that at all. It's just how you wind. You can have a shunt and a series field, and you can add them cumulatively or differentially. We unfortunately don't have a lot of time to get into that, but that's just a different type of applications. And for the group that I was in, I asked the question about, do you see a lot of DC motors anymore? And he goes, it's really phasing out. It's almost exclusively going to AC. So it used to be DC motors were great for speed control, but it's AC motors, you just put a VFD and do that. One of the things that in our group that he talked about was, did you guys go, the other groups go and look at the magnet wire when they were doing the windings of the motors? There was a big motor that there was a guy with long hair and a hat was kind of looking in. So they were doing some winding. That was just bars, but they had a bunch of boxes or pails with magnet wire, and he called it inverter duty. Does anybody know what that means? We talked a little bit about it, but there's one thing I forgot to mention. So anybody know what magnet wire is, except for the group that was with me? What's magnet wire? It actually is not magnetic at all. Wire is doing what? What is the purpose of wire? For electrical engineers. Yeah, carries current, right? That's what wire does. So really good conductors for electricity tend not to be great conductors for magnetic energy. So magnet wire is not responsible for carrying magnetic energy. It carries current. But when we have a closed loop of wire with a current flowing through it, what do we create? A magnetic field, right? So magnet wire is not magnet wire because it's magnetic energy. Magnet wire is because when I run a loop, I'm going to come basically in contact that other path that I have. So I'm physically going to come in contact with it, and then that rests on top of it. Magnet wire is insulated wire. But it's not insulated like Romex, you know, like the stuff you go buy at Home Depot with the PVC or THHN insulation. That's obvious. This is basically just like a spray-on epoxy or a dipped epoxy. So it's a small insulation, so it's very thin because the voltage between consecutive terms tends to be only a couple volts. You don't need 1,000 volt insulation for magnet wire. You just need a couple volts difference in potential between the two. So inverter duty wire, a couple things about it. So inverters, everybody know what an inverter poops out for frequency? You would know, right? Because you were going to build one. If it's a fancy inverter, right, it does a perfect sine wave. If it's a real world inverter, right, it does, you know, kind of one of these things, and you know, some spiking here and there because your diodes or your SCRs, GTOs, whatever they are, will switch on and off. So you get spikes. So your voltage will go a little bit higher. So inverter duty motor has a slightly higher voltage rating. But the biggest thing, and this is what I forgot to mention yesterday, does everybody understand how electrical insulation works? What is an insulator? Prevents the conduction of electricity through it, right? How does that do that? It prevents electrons from flowing through it, correct? Well, one way to do that is to have really tight bonding. So the electrons are in the valence shell. That's pretty much where currents flow. In copper, you have one free electron, so it doesn't take a lot of energy to move it to an adjacent one, you know, an adjacent copper atom. So insulation would have its valence shell almost completely full, but maybe one open spot. So if you look at its atomic number, its valence electrons are just about full. Its valence shell is about full, but maybe it's missing one or two. So to get one or two to move through there is very difficult. So that's an insulator. That's only part of the equation. The other thing, and this is a bigger issue, is if I have a voltage running along like this, and I don't go to a high voltage, but I do something like this, and then go like that, this voltage could be below the rating, but this dV/dt here is so high, right? It's almost infinite, that the electrons, right? Because again, this is just valence shell, it's positives and negatives. If your electrons aren't configured in a way to sort of oppose that change, they'll start to conduct through the insulation. So part of inverted duty motor is to prevent that sort of instantaneous step change, which doesn't really happen, but a rapid change when we get spikes from being propagated through the insulation. That's essentially what it is. So remember he talked about, well, I don't know, in your group, our group talked about a surge test. So you hit it with a spike essentially. That's what a surge is, right? Hit it with a big voltage, drop it off, but do it rapidly. There's a certain rate of rise. That's to verify that it operates. He also talked about a Megger test. And anybody go look at that, see what that was? Megger is just a brand name, or it was. And you used to be able to do handheld ones. It was just a hand crank, and you'd spin it, and then you had to have a needle at above a certain voltage. And I don't know what the voltages are. I think he said 2 times the voltage plus 1,000 or something like that. And you just run it at that higher voltage. So that basically says that for a short period of time, I won't get any conduction through the insulation. And so you literally are monitoring microamps, excuse me, thank you, to make sure that you actually don't get conduction. So that's a lot of the electrical stuff and how it works. Even air, right? If you try to get electrons to flow through air, there's 2 ways to do it. You can have a really high potential, or you can have a very rapid change. All right, so that rapid change is where we don't talk too much about that. Okay. Any other thoughts or comments on it? I mean, do you feel like it was worthwhile to see how motors and generators? I mean, we looked at a lot of DC motors because they call them traction motors. That's what the locomotives use. I thought it was interesting. He said 750 to 1,000 horsepower per axle, and he said most of the trains around here have 6. So that's anywhere from, what is that, 4,500 to 6,000 horsepower for a typical locomotive. And the other thing I thought was interesting too is he talked about how a locomotive engine, what does it have? It has a generator on it. That's what's out front of the engine, and it immediately gets converted to DC to drive the motors. So they still generate AC, but then they drive it all with DC. And primarily it's speed control, right? An engine doesn't run at 65 miles an hour, right? A locomotive engine, they have to be able to modulate the speed. So that's a big reason why they use DC. Now they could just use variable frequency drives and adjust it that way. So they could run 60 hertz, but keep in mind, how long have locomotive engines been around? Long time. And I think they're all electric, and they've been all electric on the East Coast for many, 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 many years. They still are diesel ones that just exclusively run diesel, and basically it's a reciprocating engine. I don't think they have coal-fired ones anymore. At least maybe they do in museums, but not actually pulling freight. So out west, where you have to go, 2,000 miles or something between stops, those would be, diesel engines that would directly drive the axles. But everything on the East Coast is electric. Anybody have a thought as to why? It's a more obvious answer than you think. What happens if you go take a train in New York City? See train tracks all over the place? It's all on the ground, right? Can you run train tracks puffing out diesel exhaust underground? You could if you want to wear masks, right, and provide your own oxygen. But when you go through big cities or get near big cities, they actually have to transition those trains to get their power not from the actual generator, but from electric wires, so you don't have the emissions. If it's outside, it's not such a big deal, but if it's going underground in a tunnel. Like, anybody know what Madison Square Garden is? What is it? It's a train station. I was a fool one time because I had to go to Queens, New York, and I was living in Baltimore at the time. I had to take the train to go to Queens, and the train dropped me off and picked me up at Penn Station, which is fine. So I remember, getting out of there and taking the subway, no problem. Then getting back, I had no idea where Penn Station was because there's no signs. Where's Penn Station? I asked a police officer, "Excuse me, sir, can you tell me where Penn Station is?" "It's right there." So I start walking towards, and I'm like, "That's Madison Square Garden. Where's Penn Station? Can you point to that to me again?" "It's right there." I don't see it. It's that building right there. See, it says Madison Square Garden. Penn Station is below Madison Square Garden. So all the train systems in New York are essentially underground. Subway, train, all that stuff. So you can see why subway systems use DC because of the old train systems. I still think most of the new ones are DC because, again, it's easy speed control. Constant power, constant torque, that type of stuff. They work pretty well. Anybody want to apply for a job or bang on some stuff? They had some nice tools there. Anybody grab any copper out of the bin, a recycle bin? Had a big box that was only about a quarter filled with clean copper. It's like $7 a pound recycled or something like that. I keep asking them to donate that to university. We'll take it off their hands, but they never do. They never give it up because that stuff is expensive. So, would you recommend us doing a tour next year? Or did you find that it was not as worthwhile? So.
The only question I was like, where does the electrical engineer fit in there? It looked like mostly mechanical stuff.
So the electrical engineer would design the windings and the mechanical parts that are not bearings and the shaft. So the mechanical engineer would figure out okay, this has to handle this load, this has to handle this weight, this has to be the shaft design. The electrical engineer would say, I need this insulation class, I need to put RTDs here, I need this many turns, I need this much permeability of the metal, all that stuff. So motors start to be a hybrid, right? Because there's a lot of mechanical parts to it. I mean, it's all mechanical, but where the work actually happens with the electrical design of the motor. And probably those motors, well, today's motors are all designed with finite element analysis, so they can check all that stuff and they can simulate it and get really precise results. I asked him if they ever did blocked rotor tests or whatever, and he said, can't do that here. We don't have the capability for it.
Well, customer, the client doesn't ask for it, we'll do it.
Right.
Okay. All right.
Yeah. So it's a commodity, right? I mean, it's funny how motors are so important, but they're just a commodity. And I don't know if your group was there or not, but we asked about what the break-even size is approximately.
I was in your group.
No, but I know you were. But I'm.
Looking at me, I was like,
No. There's other people that weren't, but we joined up at the end. And I don't remember if everybody heard. He said about 75 horsepower, where it makes sense to rewind it. That's 50 to 75, he said. And it keeps getting bigger every year because motors are just getting cheaper and cheaper and cheaper. No other comments? Concerns, questions? You want to do a lab there where I make you actually pull some of those bearings out or clean out the... Yeah, that didn't work. Well, the other thing too, they actually aren't using a sledgehammer. It looks like a sledgehammer, but it's not. Pardon? I can't hear you. I don't know what a dead blow hammer. Oh yes, I think I know its term. Yeah, it's made out of plastic or brass. Yeah. There's no bounce back, and the other thing too is if you use metal on metal, when you hit it, what happens? The metal will splay out, which you think, yeah, it's no big deal, but they were having a hard time taking a shaft out. And you got tolerances of 1/16 of an inch. Any kind of splaying or spreading out means it's the end of the shaft. So the mallet or whatever that they used was actually one that had either a hard plastic. Oftentimes they use brass. I don't know if you can find brass mallets anymore, but it's such a soft metal that when you doink it, the brass spreads. So you still get that impact that would get it to vibrate and hopefully move, but it doesn't damage the material. So they pretty quickly switched over to the puller. I don't know if anybody saw that. They hit it with a small mallet, and that didn't work. Then they hit it with a big mallet a couple times, and that didn't work. And they're like, yeah, let's get the puller and let's figure that out. So I thought that's what's better to be an engineer, because I don't do it enough. So those guys are pretty accurate. They're just hitting it like this. I'd be like smashing my fingers, and I'd be all over the place, making it not look so pretty. So last year or 2 years ago when we went, they had a nice synchronous machine, and I was actually going to show you some of the pictures that we have in the synchronous machine are the actual pictures of motors we took, that I took when I was there. So they're pretty cool about letting us take pictures there. So I thought that worked out pretty well. So nobody wanted a job. You got to bring your own tools. I did check with that. So all those toolboxes they had, those big fancy ones, they had to bring their own. Very expensive tools. See, I would have thought so too, but then I think, well, they're probably like wrenches that, like a 2-inch wrench. It's not something that you find on any local place. I could get like a car dealership where, everything is 3/4 inch drive. It's all pretty standard, but big stuff like that.
Yeah, I saw one of the soccer drivers, like over by the locomotives.
Yeah.
The head was like that big, and it was like that long.
Right. Oh yeah, you got to go buy those, because you're going to leave this company and go work on cars that have something that big. I mean,
Yeah, no, I would have thought that they would have had like some like baseline tools that were like the companies or something.
I don't know. According to what I asked the guy, I said, you got to bring your own tools. He goes, yep. He said, we give them a list. He says they don't have to have the entire list when they show up, but they have to have like the key ones, and then they eventually move up and get, within a year they have to get the rest of these tools. So maybe there's some real specialty ones, like, you said like the socket that was that big. Maybe you can't buy those, or they only need them once every blue moon. But yeah, it wouldn't be. Did he say that?
No, I said, I think they would, because they're paying you
Yeah.
to buy your own tools to work to do their job.
Well, that's the part I don't know, because think about if you're an electrician working in the field. You have to have your own dikes, you have to have your own strippers, you have to have, carpentry, right? You bring your own hammer, you bring your own drills.
I feel like that's different than like, well, I don't know, how do like car mechanics show like?
Most car mechanics, they actually have to bring their own tools.
I feel like
I don't know about the auto dealerships, because the auto dealerships, it might be that there's so much turnover in those that, they're taking people fresh out of college. And those, to be frank, I mean, a car dealership is probably the easiest place to work, because who brings their car to the car dealership? Somebody who's got it under warranty, right? Car's 3 years old. Anybody here have an older car that goes to the dealership to get it fixed? You can be honest. We won't poke too much fun. It's just it's very expensive, right? So the stuff that breaks down, it's usually the engine's really clean, nothing's really rusted on or stuck. So those are pretty simple, relatively simple tasks. It's when you got to start pulling out engines and whatnot that are in a car that's 10 years old. That's when it gets to be more difficult. But yeah, most craft jobs, you bring your own tools, right? Unless it's a really, like if you had a scanner, if you were a plumber, or not a plumber, but let's say a plumber, you're working on a furnace that has a really, specific control panel that you had to interface to, and you needed a special device to communicate. I mean, obviously they won't expect you to have one scanner for every piece of equipment you work on, but my suspicion is that's pretty common as you bring your own tools. I just would have thought a specialty shop like that, they would have had a bunch of tools that everybody shares, but that wasn't the case. I was surprised. Yeah. Yeah, most.
I work in the military, so it's different, but you have to check out everything through like a system, so they can account for every tool that checked out. It's useful for it.
Or takes it home.
Yeah, it takes it home.
Yeah. Well, the other thing too, and when you talk about the military, that's a whole different ball game, because if you think about a motor that fails at a paper mill, that's $40,000 an hour, which is expensive. But if a piece of equipment fails on the battlefield, how many lives can be lost? That's a lot more than $40,000 an hour. So you always hear the jokes about somebody paid $7,000 for a toilet seat. Well, okay, yeah, that seems like an excessive amount, but everything has to be designed to such extreme and rigid standards. When you're getting all this vibration and all this dust and debris, you don't want a 7-cent microchip to be the root cause of some military piece of equipment that's essential to saving the battlefield to fail to operate. So when you buy all the chips and stuff, everything is designed to way higher temperatures, vibration. Now it has to be radiation somewhat proof, because if you light off a certain type of weapon, you can actually emit a high enough magnetic field that all your heads-up displays, I think it's all infantry now, all have night vision goggles, right? I mean, that's standard issue. It's like generation 4. Well, what's the quickest way to make somebody blind? Take out their display. The soldier of today apparently has so much information. Well, Brian, maybe you could talk about it.
Not so much on the battlefield, but pilots, even their HUDs now, they can look down, they can see what's underneath the airplane. They won't see all this cockpit stuff. They'll look down, they can see the ground.
Oh, wow. Just by glancing down?
Yep.
There's somebody who lives in my neighborhood, and I've known him from the gym. He's a Navy SEAL, and he was talking about all the display information that's on a visor. And it's also communications too, because if you have a team and you don't communicate, how good is a team if you don't know what the other person's doing? So that's the other side of it. That's the other thing too about electric motors. So the military is looking at scrapping diesel vehicles, the smaller vehicles, and replacing them with fuel cells or something like that could use renewable energy. So one of the things is a soldier now needs something like 200 watts with all the equipment they have on it. So they're talking about little fuel cell packs, which is a canister. You just plug it in. When you're done, you just dump it on the ground and you just continue on. It's not going to be a battery, because a battery would be too heavy. So I don't know. I mean, I don't know all the infantry stuff, but I know that's the technologies really makes a big difference, supposedly. All right, let's continue on. Sorry to talk your ear off with boring stuff. So one of the things they talked about are the commutators and interpoles and all that stuff. So we'll talk a little bit about commutation in a rotating loop of wire, because if you saw the traction motors they had 4 leads. So they had plus and minus. So you wanted to get direction going. You still need to commutate that, right? You still have the motor that's rotating. You still need to flop the pole direction. So essentially, that's what commutation is. So we're going to take a look at a pretty basic 4-loop motor. You still have one north-south, and one of the things I hope you might have noticed yesterday is we simplify the diagrams dramatically here as compared to what's in the real world, because if you saw all the slots and turns, it's really difficult to figure out where the norths and south are. But let's just simplify that, right? Let's just say we have one north on this side and one south on the right-hand side. And on our field winding, we're going to have 4 loops of wire. So what you have, and it's a little hard to see, this is A1, and then it comes out and connects to this commutator section, which goes to the plus lead. The return path is in the dotted end, right? So this is coming out at you. This is the going in. So 1 to 1 prime is one winding, right? Anybody understand why it goes into the page or into the screen like it does? Remember how our magnetic field has to be cut by the wire? So if this just ran on the surface, that's outside the north-south, right? It goes back into the page because the north-south goes back into the page. You have magnetic fields going this way. So 1 to 1 prime is one wire. 2 to 2 prime is another wire. 3 to 3 prime, and 4 to 4 prime are the wires. And you will note this is the brush, this right, is the commutator. You have 4 separate sections, right? 1, 2, 3, 4. We only have 2 brushes. Why do we only have 2 brushes? Any thoughts?
Wait, so those commutative sections are like the little copper and the stuff?
Exactly. Yeah, so if you looked, you remember on the motor, you could see where the windings went in, and then on the tip were the straight copper sections. Those are commutators. So that is the commutator. This is rotating along. So I have 4 of those and 2 brushes. Why do I only have 2 brushes? Exactly. You only have a plus and a minus DC, right? So I only need the plus and the minus to connect as necessary. And as long as I've only got this level of spacing, I don't have to worry about bouncing around and saying, hey, I need to move this up and down. So I'll just take my brushes, and if I need to space these out differently, I'll just change this wire, right? I'll move this in and out as necessary. You'll notice how 3' connects to 4. That has not a heck of a lot to do with it. All it's saying is the positive or the negative is going to be connected to here, and the opposite is going to be connected to 3. Okay? So you don't get current going from here, from 3 through here, and then into 4. It's basically parallel paths. So if you're trying to envision what's happening, oh, there's my pencil. All it is essentially I've got a winding here and a winding here. Those are separate. So these are close enough that I have plus DC over here, and these are close enough that I have minus DC over here. They're essentially in parallel, right? That's all that means. And what happens is by spacing these out and connecting these things, the 3' to the 4, I'm getting a 90-degree separation, which is going to allow the machine to rotate, okay? It's going to allow it to rotate. All right? Let's see, any questions? So, one of the last things, we machined them, right? You notice how all the machines, they were all perfectly circular. And again, that's for uniform air gap, right? We want to make sure that each winding has exceeds the same MMF because we want nice, smooth operation. So let's take that and let's take a picture and let's sort of break it out. So now what we've done is we're looking on the top of the motor and we've sort of laid it out flat to get this section, okay? So this shows the commutator sections, A, B, C, D, and then back to A, B, C, and then continue with D. And then these are the brushes, plus, minus would go in that manner. We also see the pole faces and the wires. So we have 3, 1, 2, 4. Notice we don't have the primes, right? Because this shows the entire, whoops. Let's see, let's go this one. This shows the entire in and out of the wire. So this is actually a better understanding of how the machines are actually wired up, right? Because you can see this wire 2 comes in here, goes down, and then goes to my C commutator, but heads back into the motor, goes under the south, and connects to 3. And it just keeps repeating, right? Just keep wrapping it around. So that's exactly what they're doing in the machine. They're just wrapping a wire around, and you have it demonstrated that way. This shows 1 loop, but you could have 50 turns in that 1 wire. That's perfectly fine. Okay? All right, so let's see. So we'll show this particular instance where 1, 2, 3', and 4', those ends are under the North Pole, and 1', 2', 3, and 4 are under the South Pole. So we're going to get a voltage using our E induced is V crossed into B, dotted into L. Again, everything is perpendicular and parallel. So all I have is VBL, and my voltage is positive out of the page. So what that means is the winding itself is going to see a plus, and into the board is the minus, right? So the cross the wire, which is here, you would go plus to minus, is how that voltage is across that lead. And let's see, and then the opposite would be EVBL, but the opposite is the positive is into the page based on the rotation and voltage or velocity crossed into my magnetic field. Now, so let's redraw those. Now I've got all my windings, and I'm just going to show them in line, basically two-dimensional, and this represents that three-dimensional wire going in, but I've got individual voltage drops across each of those loops of wire now. So what I have is from winding 1 to 1 prime, I have a plus minus and a plus minus across the coil. This is the back side, right? That's the other side of the motor. I can do the same thing from 2 to 2 prime, 3 to 3 prime, and 4 to 4 prime. And then this shows you the commutator with the plus minus here, right? If I sum these, right, I go minus the plus, work all the way around, the voltage across here is equal to 4 times that little value of E, right? Because I've got 1, 2, 3, 4, and 1, 2, 3, 4. So the potential difference that I see is 4 times that individual voltage that I generate across each lead, each winding. All right? That's at omega t equals 0 degrees, right? So basically the rotation point is here where I get 0 degrees. Let's see, I've got these two parallel paths for currents through the machine, right? I have path 1 or path 2. Either one of those are parallel and through there. These two, though, have no path, right? Which is fine because I want to make sure that I have my current flow that goes all the way through plus to minus. I don't want to short circuit out or bypass any of the winding because I'm trying to get a lot of magnetic field and rotation out of this particular unit. So now let's rotate 45 degrees. I wish I'd have my pointer because I have to stand by my computer and I still haven't found my clicker piece. So as my motor continues to rotate, right? So now I'm rotating 45 degrees, and you'll notice now that the 1 and the 3 windings are perpendicular to the north and the south. What about the 2 and the 4? They're parallel. So do I have any power or any magnetic field that's being cut by those loops of wire? Not a stitch. So look at the 0 volts across 1 and 3. See that? Does that make sense? Don't make sense? You can see I get no voltage that's being produced by those loops of wire. So the only voltage I'm going to get is 2 times my voltage, right? Because half of it is not contributing in any way, shape, or form. I'm not producing any voltage E in those windings. So that's the reason why this functions as it shows. Now this shows a little bit with the magnetic fields, and it's not being perfect, right? Because you can see sort of I've got this guy going across this way and this one kind of going across this way because it's not a perfect north-south, but that's essentially what I'm getting. Whoops. So over here, I also forgot to mention, This is okay, right? Because I've got no voltage in some and I've got some voltage in the other. So at this point, I'm just going to short circuit across those two. I can short out both of those commutator sections with the brushes. So I'm going to allow the flipping of direction. It's okay to do that. And that only happens, and here's the thing, when I have 0 volts. When I have 0 volts, it's no big deal. There's no potential difference between the two, and I stop those. Do you remember, or maybe you all remember when he talked about what an interpole is? Interpole is basically a pole sort of in between the two poles. The reason you need that is because how often is it going to be exactly at 0 volts when you commutate? It's never going to be at 0 volts, right? Or only very briefly. So that interpole is going to allow you to generate an opposing voltage to minimize the voltage difference between the two separate commutating strips. And then that way you can kind of cancel it out. So in a real world machine, you need those interpoles unless it's a small enough arcing that you won't have an issue. So every time you go across a commutator and you switch, you get a slight arc. Unless you have an interpole, which reduces that significantly. So that's essentially what the commutator does. It allows a switching of pole when the voltage is approximately 0 across the adjacent windings. So we rotate another 45 degrees and we're back to that same voltage. 4 times my individual voltage. Everything has flip-flopped. It's the same result. And here's what the actual voltage across those brushes is going to be. Start out at 4 times the individual EMF voltage that you would get under one winding. Goes down to 2E. Then as it rotates, it goes back up to 4E. Notice it's always positive. And the reason why it's always positive is because I've flipped, right? The commutator has flipped to the next winding. Well, the brushes has made it so that the commutator flips. So this is the output of a DC machine. Not a perfect DC by any stretch, but you notice it's pretty close. So you could do some smoothing, you can get it to be closer. So this is how DC machines function. Just really take the alternating current concept and flip it around by using brushes and a commutator, and that's how you get operation. That's how it actually functions as a commutator. Questions? It's kind of esoteric material, and there's a lot of faces like, what's going on? But the key thing is our magnetic field, does it cut it? What's the voltage across each individual coil? How are they summed up? And then when we switch or rotate with the commutator, how we go back up to that 4 times the individual voltage E. No questions? Questions? Keep going.
Unless you want to stop.
Why, you want to stop and go out in the beautiful weather? Well, I've only got 2 more classes. So that's commutation, right? So, sort of summarizing that last paragraph. The voltage wants to go from 4E to 2E to negative 2E to negative 4E, but we stop it by switching the direction. We force it to be back to a positive E, or 2E and 4E, and that's commutation. So it really is kind of being sneaky with a DC machine. It's basically an AC machine that we've sneaked into it by using those brushes and the commutator. And that's all it is. All right? So, what are the issues with commutation? I don't know why I have 3 in there. It should only be 2 because armature reaction is twice. So let's take out the second one, the third one. So we have 2 issues. We have armature reaction and LDI/dt voltages. The first one is not as obvious, but essentially we're going to get current flow in our armature, and any current flow is going to produce a magnetic field, and that's that armature reaction. The other one is when we have our brushes and our commutator, when we're trying to swap directions on our magnetic field. Well, we have a big inductor that we're trying to swap directions on. Well, that does not make the inductor happy, right? You don't want to have those change. So that's why that LDI/dt is a problem. You're going to generate spiky voltages to go ahead and prevent the changes in voltages. So those are 2 issues with the commutator. And you'll also notice too, the voltage is doing what? It's rectified, right? So the actual DC machine was the one, when we talk about a full wave rectifier bridge, that actually came from the concept of a DC machine. It rectifies the issue that the output of that machine would normally be AC and converts it to DC, right? Why would anybody call a full wave rectifier? Where does that come from? Doesn't make a lot of sense, right? But if somebody way back in the day said, darn it, I've got an AC output, but I need a DC output. Well, let's put this commutator on here to rectify that fact. Fix it, right, is another way to say it. That's where the rectifier comes from. It just fixes the problem. Same thing with the diode bridge. It fixes the problem. Let's see. So if we connect a load, now we're going to get a current flowing in the armature winding because we have a voltage, right? We have a voltage on the armature. We got a load connected to it. It's going to do that. With our current flow, now we're going to get armature reaction. That armature reaction is increased as we increase or decrease the load, depending on your perspective, right? If you put a smaller impedance, you get more current. But that is effectively the same thing as actually increasing the load. The neutral plane shift, that's sort of an interesting topic. But in a DC machine, you have a neutral plane, which is neither positive nor negative. It's not ground. It's not neither positive or negative. What ends up happening is that the plane of where your plus minus actually will shift depending upon this armature reaction. So you actually don't get a real plus minus like you would expect. The difference between the plus and the neutral and the minus and the neutral is not the same. Okay? So that's part of the issue with my neutral plane shift. It shifts up towards the positive or down towards the negative depending upon the armature reaction. This sort of shows you schematically what's happening with our neutral plane. You can see our magnetic neutral plane is north-south, so figure A shows the difference between the north and the south. It's just a straight line directly through the center. Now as I rotate my my rotor circuit, you can actually see how the wire wraps down. Notice it's not straight across because that MMF wants to stay uniform, right? See the air gap? The air is way more conductive and the iron through the core is way more conductive than if things went off straight. That's why things sort of peel in towards the middle to be parallel, right? They want to go through the shortest distance. The only reason why these are this way, because that's a shorter distance than this, isn't it? The shortest path between those two is to take the perpendicular or tangential, maybe that's a better way to say it, the tangential point between those two. And that's why those curved lines go. Move on to C. Now we see we've got a north and a south pole. We've got the overall magnetic flux flow in the north and the south as shown. Then we move over to D. Now we actually start to get some armature field reacting with our magnetic field. So if you see here, this is the armature field. This is the magnetic field that goes from the north and south. So what ends up happening is, here's my old neutral plane, original, and I tilt this way because of my armature reaction. So what that means is now I don't have a definitive, because it's plus minus here, right in the center. So I have issues with that plus minus being perfectly balanced between the 2 points. Okay? So that is an issue with neutral plane shifting, particularly with DC motors. So let's see if there's nothing specific that I haven't talked about already here is exactly vertical at this stage. So let's continue on. That shows the effect. Now it pulls it, right? So it's sort of explaining it, how it interacts, and the magnetic field pulls it on in that direction, and it's shifted direction. So if it's a motor, the current direction is reverse, and we get the exact opposite, right? The shift depends on that rotor current, and thereby the load of the machine. If the brushes are set to short out the conductors in the vertical plane, then the voltages between the vertical sections and the commutator are 0. When my neutral shift occurs, it's no longer 0, so now I got a voltage across them. And that's when I get sparking across the brushes. That's when we talk about our drills and we get all kinds of issues. The pitting of the commutator segments, right, so those are those copper bars, anytime you have arcs, that means current is flowing where you don't expect it to occur, so you get pitting, and that's when they wear really quickly. Oops, I hit the right button, there we go. So air, I always like this, air near the brushes in a machine is normally ionized because of that sparking air. And that's when flashover occurs between adjacent segments. So you literally can flash over through the ionizing air because of a problem with neutral shift, right? So one of the reasons why they have fans on these motors helps keep them cool, but it also makes sure that you don't have ionized air going through there. The quickest way to get rid of ionized air is to blow it out of there, right? If you have to deal with air, just blow it out. Just keep the air volume high enough to prevent it from causing an issue. You can also get some flux weakening. So we've talked a little bit about how when a machine has magnetic field, it tends to be operated at its saturation point or someplace on the curve. So when the pole adds MMF, you can get to either an average flux that's either increased or decreased. It just depends on, where you are operating of the motor. Okay? So you can actually go up or down relative to where you are on your operation. And this shows the flux under the pole faces. So the first one tries to show you what it would look like, sort of in a more ideal world where you have that specific value. In the next case, you actually see what's happening to the flux with a neutral point shift. So look how it's actually changed. It's no longer a nice flat and then quickly goes down. You actually get that sort of slewed to the right, or skewed to the right, and then it goes down. So if I was trying to get DC out of this particular machine, this is not an easy thing. It's a pretty ugly representation of that. So flux weakening causes problems both in generators and motors. All you need to do, if you're okay with it, is you just reduce your voltage, and then that sort of adjusts for the armature reaction that you have. If you have a motor, it's a lot more serious. So if your flux decreases, it runs at a faster rate. And let's see. So we talked a little bit about shunt and series, and I didn't put that up yet. So a shunt series machine. So we have this is our stationary part with a bunch of windings on here. This is the rotating part. This is the armature winding. And this is the field winding. If it's a motor, you connect this plus to minus, and you still need a field over here. If it's connected in shunt, that's a shunt connected DC machine. You just take the armature and take the field winding and put it in parallel. So as the speed or the power demand increases or decreases, there's no change over here, right? So as I put more mechanical load on here, I get more current flow through here, but that doesn't affect the field at all. So this is one where you say, well, as I increase the load, the speed is going to stay fairly constant. The other option I can have, so that's a shunt design. This is a series design. You actually put it in series. So under very lightly loaded conditions, it puts very little field energy because there's very little current through it. As you put more current through here, you get more field, right? So in series connected, they tend to speed up. The more load, the faster they go. So that's series versus shunt. And then you can also go compounded. What do you think compounded means? Both, yeah, exactly. You take the series winding and the shunt winding, and, well, you've got both. You've got a series and shunt. So you can connect a separate set of windings, and you can add those in shunt or series. And you can have them compounded cumulatively or differentially. It just depends on which way you want to go. And sometimes you can't tell. Sometimes you energize it and it's cumulative, sometimes it's differential. How do you think you can tell if it's cumulative or differential? You turn it on, you add load, does it speed up or does it slow down, right? If it slows down, it's differential. If it speeds up, it's cumulatively compound. They're aiding each other, they're helping each other out. So that's where we talk about this runaway condition. It just keeps increasing as you increase the load because those fields are constant. They don't change. And this is the LDIDT change, right? So we're trying to get this positive 200 amps to immediately go in the opposite direction. So I go from 200 amps to minus 200 amps through that same coil of winder because I'm trying to reverse direction. And this is happening through the width of the brush. And that happens in 1.5 milliseconds. So you can see, right, you don't have an instantaneous change. You can see that that sort of smoothing out until it sparks because it's starting to pull away, right? Because it still hasn't gone to minus 200, and then it jumps because of the spark over to the minus 200 amps. And then just this talks about how quickly, right? So we have 400 amps, right? Because we're going from plus 200 to minus 200. If my machine is spinning at 800 RPM and there's 50 commutator segment, we're going to say that it takes about 1.5 milliseconds to transition. Look at the relative change in current, 266.7 thousand amps per second change. you can see why LDIDT would be a problem, because look at the size of DIDT. It's pretty dramatic. So because of that, any L that we have whatsoever is going to produce that high voltage, and we're going to get a spark across the brushes. So you can do brush shifting, right? Which basically means you tilt the brushes a little bit and you get a little bit length of doing that. The most common one is the interpole, which again is going to have a pole that is going to introduce an opposite voltage to change that, or you can use compensating windings. Let's see, so we did neutral plane shifts and we would try to adjust the brushes, but that aggravates that flux weakening. Oh. Is that the last of the slides? Oh, that's it. I guess I didn't get all the slides in there. Well, what's going on? Hold on just a second. Yeah, that was the last slide that I had, so I guess I'm done for the day. So you get your wish. So on Thursday, we'll kind of do a semester review. We'll talk a little bit about what will be on the final exam. We'll do, so there's two separate versions of evaluations, right? There's the online one that you should have access to already. Everybody knows you can go to Blackboard. I think I've seen people actually do that, but if, in case you have, well, I haven't seen it. It just tells me a response rate. I don't actually see your responses, so don't get nervous. But it does say that some people have already had access to it. It's been turned on since the 23rd, I think. But there is something for our assessment stuff for this class, so that'll be a separate sheet, so I'll give you some time. So the biggest thing for Thursday's class is come prepared with any questions on the final. Already written the final. It is comprehensive. It's not going to cover a ton of DC machines. This is just because we had an extra class and a half or so to talk a little bit about DC machines. We'll cover that, but we're not. I don't care so much about it. I just really want you to understand commutation, brushes, interpoles, at least understand the concepts of it. It's really going to focus on three-phase power, transformers, induction machines, and synchronous machines, right? Those, well, an AC circuit analysis, but that's stuff you probably learned from your previous circuit analysis class.
How many questions are there?
6, I think.
Do they all have like multiple parts?
If it is, it's only 2 or 3 multiple parts. It's not going to be like you'd have 8 or 9 parts for a problem. I'm trying to break them up into smaller parts so that if you make a mistake on part A, it doesn't, you don't have 10 other parts for it to manifest through.
So not A through O.
Right off the A through O. I only did that on the homework, right? I didn't do that on a test. Maybe A through F on a test, hopefully, but that's about it. Anything else? All right, well, I hope you enjoy your main day tomorrow. Somebody said it's supposed to be 81 degrees for a high, so get the suntan lotion out.
Definitely gonna be nice.